So this is Module 10, looking at exponential functions as we move to close up the algebra portion of this course. So we want to start with understanding, well, what really is an exponential function. Well, what's an exponent? An exponent is we have a number, and the exponent is the little number up here. And when we see this, what does this mean? This is going to indicate repeated multiplication. So this little 4 says take the base, which we call the 3, and multiply it 4 times. So that's the operation of exponents, right? 3 times 3 is 9, times 3 more is 27, times 3 more is 81. So that's what an exponent does. What an exponential function is the exponent itself is where the variable is. So this can be a varying value. And so we have this idea, it means to repeat multiplication by 3 many times, but x is not limited to being just an integer value, a positive integer. It could be a negative integer, and it also could be a decimal value, a fractional value. And so what does that mean? What would it mean to multiply by 3.5 times? What's a half of a 3? So that's where we get into things like square roots. So it does open up a lot of different thinking. We've got the basic idea. It's multiplying by a certain number of times, but when it becomes a decimal, it's a little bit more abstract. But all of those are in there. And so what we end up having is that we define the exponential function to be some number. A is a base, and we've got some limitations on what a can be, but a is a real number. It could be 1, 2, 3, 4, 5. Well, actually, it can't be 1, right? Right here. There's a reason we don't want it to be 1. It's not that it's it can't be done, right? 1 to the 4th power. 1 times 1 times 1 times 1. It's just that when this happens, we stay at 1 because 1 times anything is itself, and 1 times 1 is still 1. So it doesn't have the features of what we think of what we define an exponential function to be. So we say this is too simple. This is really a linear function, right? So we don't have the base be 1. There's another reason. Another thing we have to consider is that the base itself. Why don't we use b for base? I don't know, sometimes we do. Anyway, it's just a marker. It's what we call a sort of a constant variable, more of an unknown. Once we decide what a is, it's fixed, right? In this function, a will be a number that gets fixed. X is the thing that will vary. Its input will vary, and therefore the output, the y value, right? This is our y value, will vary. So x and y are over here. A will be a particular number. And the reason why a has to be greater than 0 is, let's look what happens when if we were to have a negative base. So I have -2. Watch what happens. I'll square it. -2 squared is -2 times -2, which gives us a +4. But if I take -2 and I cube it, take it to the 3rd power, then I'm going to get -8. So notice how this output, remember these are y values, they're jumping between positive values and negative values. The graph would be so disconnected. And one more thing, if I do -2 to the 1/2 power, we'll see that this is actually the square root function. And so what is the square root of -2? Well, it's an imaginary number. It's the square root of 2, whatever that is, it's a decimal, right? So we're jumping between real numbers, real positives, real negatives, and imaginaries, back and forth and all around. So it's not a well-defined function. So for that reason, we leave A. We just say, nope, that's not what we're talking about. A has to be a positive number. Now, we can write it this way, -2 squared. This is an okay function. We're going to see, and this is actually a translation. We'll look at that. But what's happening here is order of operations say we do the exponent first, and then we apply the negative outside. So notice the difference of where the parentheses are. So whenever you write -2 squared, what's going to happen is the exponent gets applied first, right? Parentheses, exponents, multiplication, division, addition, subtraction. That's PEMDAS, right? The way we've been taught. Order of operations. Negation is actually even after addition and subtraction. So it's kind of like the last thing that gets done. So that's how that is. And your calculator will tell you the difference. Enter this here and enter this, and you'll see you'll get a different answer. This actually ends up being -4 because you square it first and then apply the negative. This one, the negative is getting multiplied in here, so it's a +4. Okay, so that's our understanding, the basics of what happens with exponential functions. Now we're going to look at it just kind of accepting that this has to happen. The base has to be positive. Can be a fraction, can be a decimal, can be anything, but it has to be greater than 0. And again, 0 is not a valid thing because 0 to any power is still 0. So again, it's just like 1. It's sort of so boring. It doesn't have the features of what we think an exponential function should have, or not just think, but define it to be. Okay, so we're not going to use 0. We're not going to use 1. We're not going to use negative numbers. Okay, so let's go ahead and take a look at a graph, and we'll kind of do this in an exploratory way, and then we'll come back and we'll actually have a definition of it. So here's decimals, and we're going to look at just a simple function of 3 raised to the x power. Okay, 3 is not 1, it's not 0, it's not negative. But when we do this, we get this sort of a graph. Okay, so this is and what we're going to find out is exponentials are, at least for this time, for what we just explore in this class, it is going to be the fastest growing function we know. We'll see a feature that we always have the 0.01 here, because when an exponent is 0, anything to the 0 power equals 1. Okay, so 3 to the 0 is 1. There's one exception, and that's 0 to the 0, but we've already taken care of that. We're not going to put 0 here. Let me show you also, we can use a table. So I'm going to change this a little bit. We're just going to do x, and this will be f of x. And I'll show you, we can plug in values here. So let's put in x as -2. Here we go. I lost my pointer. So I'm going to put in -2. Oops, not there. Sorry. That's going to be x. This will -2. And we see we got 0.111, and there's that part of the graph. And we don't have to go in order. We could go back and say, well, what if I put in -9? We get a very small number. So this is this is in scientific notation, right? 10 to the -5 means you move the decimal to the left 5 places, so you have 0.000005. So you have a lot of zeros anyway. We see we're getting very close to 0, but actually we will never get equal to 0. So that this axis here is a horizontal asymptote. Okay, it's a line we get closer and closer together to. So y equals 0, that is a place where the graph doesn't actually touch. We've also seen we've got this point here, the point 0, 1. That's on the graph, and then it's going up. And we can come back here, and we can put in other values. I didn't know it could do that. Go to the next one. It jumps around, but we see we're getting very, very small, but not 0. So let's see what happens on the other side. If I put in 1, I get 3. If I put in 0, I get 1. Okay, and it's actually plotting those points for us. Put in 2. Wait, how could you get, 3 to the second power is 9. So we get fairly big, fairly fast. Okay, and if we put in 5, we get really, well, anyway, we want to get bigger, bigger, bigger. Put in 10, we get big relatively quickly because what we're changing, the variable that gets changed is this exponent. And just to show you a little bit, I'll go from 0 here. I'll put 1 in. We'll do a 0.5. That's a 1/2, which is the square root of 3. So you could put that in, and you can see that the 1/2 power gives us the square root of 3. And that would be, that's 2. That would be that point right here. Okay, so we can explore exponential functions. And we'll return to our presentation here, and we've got a little picture here of it with the features, 3 to the x. The domain, actually, we can put in all x values from -infinity to +infinity. The range, the y values, again, it's never equal to 0. It's always just a little bit bigger than 0. So that's that horizontal asymptote there of y equals 0. It does have a y-intercept of 0, 1. We'll see all base exponential functions will have this. Now there's a way, we'll see. We can change what the y-intercept is by doing a translation of this basic graph, and we're going to do that. We've got our horizontal asymptote. We've talked about that. It's a line that it gets closer and closer to, but doesn't touch. Now, we'll talk more about asymptotes later. The graph is increasing, and we see that all bases have to be greater. This is what we will see as long as the base is greater than 1. But that raises the question, what about, remember, we said it can't be 1 and it can't be 0, but it could be between 0 and 1, which would be a decimal, right? Anything smaller than 1 is going to be a fraction from 1 to 0. Okay, so let's take a look at what that would look like. So what about the reciprocal base of 3? So reciprocal would be, so think of this as 3 over 1, right? You could think of it this way. So what about 1 over 3? What would that look like? So that's a number, now our base is bigger than 0 but less than 1. What does that look like? Well, again, let's explore a little bit with the use of decimals. Let's go there then. I'm going to get rid of all these dots. Let me clear off the screen of these. And I'm going to leave this one here. And we're going to see, we'll get a new function, g of x. We'll do this one to be 1/3 raised, not there, 1/3 raised to the x power. There we go. It goes the other direction. Let's go with blue. I like to change colors. Colorful, right? Notice it's a decreasing function. It has the same y-intercept of 0, 1. It has the same horizontal asymptote of y equals 0. It really behaves exactly the same way, but it's a reciprocal function. And that's occurring because another way to write 1/3 x, another way we could have written it is as 3 to the minus x. So when you have a negative exponent, the way to make it a positive exponent is to move it down into the basement. So this becomes 3 to the positive x, 1 over 3 to the positive x. And then with exponent rules, you could see we could easily, because x to the 1 to the x power is still 1, so it's equivalent to this. And again, a way to show that is simply to graph it. So we'll go ahead and just do y equals 3 raised to the negative x power. Okay, and we'll do it in green. There we go. So that we can see it's right on top. Turn it off. There it is, the blue one. So these two functions are the same. 1/3 x, 3 to the negative x. Okay. So that's another function that we will be working with. And we'll come back to this. So the reciprocal base, 1/3. So here's all the details. Again, these are in the notes as well. And we just sort of explored it. It really is a reflection around the y-axis of the f of x 3 to the x. Okay. So we see this happening whenever our base is between 0 and 1. We're going to get a decreasing exponential function. So we always think of it, when we use the word exponential growth, we're thinking, oh, it's very, very fast growth. Well, that's true, but it's also very, very fast decreasing as well. If we have a value less than 1 but greater than 0. So that's how it works with the reciprocal functions. And again, the way this happens is a negative exponent. So it is a reflection around the y-axis. Okay. Let's look at another feature. How about vertical translations? Vertical is up or down, moving it up or down. How do we make that happen? Again, we'll go back over to Desmos. I guess it only lets me have a few open, so anyway, I got here. So how do we translate this? And I'll go ahead and leave this here. So what if we take f of x and make it equal, or actually, let's do it this way. Let's say y is equal to the function f of x plus 2. What's going to happen? What's going to happen here? It's going to move it up 2. So it's taking this x plus 3 and it moved it up 2. And notice what happened to our y-intercept. It's now at 3. So 2 higher. Every point on the red graph, in fact, maybe I can turn this blue graph off, has now been moved up 2. So any point that is on this red graph is now 2 higher. So this is 2 higher. You can see it. It's harder to see over here how it when it goes up, but that's exactly what's happening. We've just translated it upwards by 2. And even when we come up here, again, each x point here is 2 higher here. They seem to get closer and closer together because the numbers are getting so big. When you're at 1,000,000, the difference between 1,000,000 and 1,000,002 is not going to be as obvious as the difference between 1 and 3, right? That's 2 higher. So that's the visual look of it. But that's how we can get a translation, okay, vertical translation. We're going to look at other things. So here, if we add something to the function, 3x plus 2, we've moved everything up 2. And what we've also done is we've moved our horizontal asymptote from y equals 0 to y equals 2. And so our range now only goes down to 2. It doesn't actually equal 2, right? 2 is not included. It's just a little bit bigger than 2. Our y-intercept has changed. So that's another feature as we start looking at exponential functions. Okay, so that's a vertical translation. What about horizontal translations? How do we make those things happen? Well, if you remember, I think it was back in Module 4, let's get rid of some of these things. We looked at different translations with other types of graphs. Let's get rid of all of this. And what we found is if you add or subtract inside the function, so this will be f of, notice we're inside the function, let's go with x plus 4. Notice what we've done is we've moved to the left, sort of in the negative direction 4. So whatever this point is here, 0.633, that's a hard one to take a look at. Let's see, how about this one? 2, remember, equals 9. When x is 2, y is 9. And now what we've done is we've basically, think of subtracting 4. This is now that negative 2 is equal to 9. There it is, negative 2 equals 9. So we've translated to the left. If we want to translate to the right, we change to a negative. And notice now the function's over here. So instead of 2 being the value that gives us 9, right, what we have is it's going to be 6, exponent of 6, because you put in 6, subtract 4, you get 2. So this is the function. With this function notation, x minus 4 goes up here. This is the function 3 raised to the x minus 4. So we're doing the subtraction up in the exponent. So f of x minus 4 equals this. Vertical translation. And again, it doesn't do anything to the range. The range still goes down to 0. Doesn't do anything to the domain because the domain is still from negative infinity to infinity. We can plug in any x value. But notice it is translated horizontally. So that can happen with exponential functions. And we have one special base that we use, and that's e. E as a number. So think of it as in terms of something we might be familiar with from geometry. We've got the number pi. We write it as a letter. This is actually a Greek letter, so we usually don't associate with anything else. But it's the number 3.14. I think it's 16. It's got a lot of different numbers, but most of us, or at least we remember it as 3.14 and maybe use it. But remember, this is a number that goes on forever without repeating. And e is a similar type number. And if you put it in your calculator, you can go e to the first power. It's the number, I think it's about 2.718. So a lot of times we'll write it as 2.72. We round it. But again, it is a number that does not repeat and does not terminate either. It goes on forever and ever and ever. But it's called the natural number because it does occur in nature and it has some very special characteristics. So we end up using it quite a bit in exponential functions. And so just to introduce you to it, it's going to look very close to the 3 to the x graph, because notice it is close to 3. It's 2.72 if we want to round it. So this gets me there. we don't like that one, but let's go back to our original. Again, let me clear this stuff out. And I'm going to graph right on this same one here. Let's graph the function y equals, you could do g of x if you want, y equals e, and notice there's that number 2.71. So the calculator knows that that's not a letter. It's not a, well, it's a letter, but it's not a variable. It is an actual number. But you don't want to have to write this out every time, so we just do e, and the calculator knows what it's doing, and we raise it to the x power. And notice it's very close to being, it's a similar function to 3 to the x. Okay. What's confusing me is, let's do y equals 2 raised to the x. Oh, I see what's going on. Okay, so what was kind of confusing me is it's sort of this optical thing. It looks like e to the x was, for some reason, looks like it was getting bigger faster, but it takes a bigger x to get to the same y. Okay, so this is, but we can see the blue one, the blue graph. This is y equals 2 to the x. This graph here is y equals e to the x, and the red one is y equals 3 to the x. So we see as the base becomes larger and larger, it increases faster, which makes sense with the way that exponentials work, and that e is a number somewhere between 2 and 3, closer to 3 than it is to 2. And again, because if we were to write this out as a number, it's 2.7. I'm just going to round it to 2 decimal places, but that's not very accurate. As we saw, approximately. I should not put equals. I put these little squigglies, and that means approximately. Okay. So that's another one that we use quite often. So you're going to be working with e, but you have to see it as a number, just as if it was 2 or 3. And for all purposes, we can think of 3 to the x as, e to the x is close to that, at least in these early stages. Again, the larger the value of the exponent, the further distance they are apart. Okay, so that's our other one. So we're just sort of defining functions, and then that's our natural base. And then we're going to look at one type of question. A lot of the questions you're going to face are how to evaluate an exponential function. So we're going to do this both graphically and algebraically. So here's one that's an exponential process. We notice that this has a negative exponent, and remember, with a negative exponent, we end up decreasing because it's really the reciprocal function. So this is decreasing. Can of soda is placed inside a cooler. Cool. As the soda cools, its temperature in degrees Celsius given by the following function, where x is the number of minutes since the can was placed in the cooler, is this. So we can see it as we put it in the refrigerator, it starts to get cooler. Okay, so what they're asking us to find the initial temperature of the soda. So what does it mean in terms of what is the value we would use for the initial temperature? Well, that's right when we place it inside at time 0, right? X is the number of minutes, X is time. So what we really want to find is the initial value when X is 0. So we can do it this way, and this is really a nice feature of exponentials. It's relatively easy to calculate the initial value. Minus 0.028, and we're plugging in 0 for x. And you got to be careful sometimes, depending upon your calculator, you might need a parentheses around this, because remember, it always applies the exponent first and then does multiplication second. So we want it to do the multiplication within the exponent. 0 times negative 0.28. That's going to give us 0. E to the 0, remember everything to the 0 power except 0 itself, is equal to 1. So this becomes negative 8 plus 24 times 1, right? E to the 0 is 1. And so this is now not an exponential, it's just an arithmetic problem. Negative 8 plus 24 is going to tell us that that was 16 degrees Celsius. Which with Celsius, remember, 0 is freezing. So it's not freezing, it's, let's see if we convert this, I think it's like 60 some degrees. See, if you multiply by 2, you get 32. You add 32, you get about 64 degrees. It's got a little error in there, but it's in the 60s. Okay, we're going to cool it down. So after 15 minutes, what is the temperature? Okay, so we do the same thing. What we do is we plug in, since x is in minutes, we plug in 15 for x. Oops. .028 times 15, not negative 15, positive 15. Okay. And we can pull up our, it's a good place, we'll do it with just our graphing calculator, or any calculator. So we just put in negative 8. Now there's two types of negatives, sort of. There's a negative, there's a subtraction key. We want negative 8 plus 24 E, and the E button on this calculator is right above the ln key. We're going to talk about what ln is. It's the natural logarithms. We'll get into those in the next few lessons. So we have to use the second button. This gives us E. And notice up here it's going to give us the exponent. So we're okay. If you have an older version, it might be using, an older version might have, in fact, I'm not quite sure how to get back into the older mode, but you might need to put a parenthesis around your inputs. I'm going to go ahead and do it just to be safe, even though this calculator will put it in correctly for me. And then we do times 15. And it will say after 15 minutes, we're already down to 7.8. Set T of 15 after 15 minutes, 7.8 degrees Celsius. Okay, and that's probably getting cool, almost cool enough to drink. That was a pretty quick drop. About 16, 8 degrees, something like that. This is about 8. So a little bit more than 8 degrees Celsius in just 15 minutes. Quick cooler. Yeah, to the nearest degree, actually, I guess, if you follow the instructions, they want the nearest degree. So we better round this to 8. Instead of 7.8, we'll round it to 8 degrees. 16 degrees. All right, so that's how we evaluate a exponential function. And again, you could do it with we don't really need a graphing calculator. What we use the graphing calculator for, if we say, okay, I want mine to be really cold, so I'm going to follow this along, and I'd like it to get down to not quite freezing, because you don't want it to be ice, right? But let's say we wanted 3 degrees Celsius. We want to find out when will it be 3 degrees Celsius. Then what we need to do is take our function and we need to solve for x. We're going to find some methods for doing that in the next few lessons using logarithms, and that's okay. But we can also do it graphically. So what we're doing, we're going to go into Desmos. We're going to graph each of these equations. I'll graph this as one function and this as another. Now in the TI calculator, they label each of the graphs. So this one might be like y1, and this one would be like y2. So we could put those in there. It's going to show up a little bit better if I use Desmos. So I could use this one. Why not? We could use Desmos. I'll do them both real quick. See, I was doing something over here anyway. So I'll clear out these. So what I did is I hit the y equals. That gets me here. I'm going to put y1 as y equals 3. And what you're going to see is that's a horizontal line. Y is always equal to 3. In the second one, I'm going to put my function minus 8 plus 24. And remember, to get e, I have to go second, and then this button down here, get me e to the x. It gives me my exponent. Again, some of you might have a little caret there, and then you need to put a parentheses, and then I put in my exponent, negative 0.028, and then I put in my x, which is up here is the variable key, and so it'll graph that. I'm just going to go ahead and go to the graph. I'll show you. We don't see, so this is cooling down, and you might, let me do this. I'm going to go to a zoom standard. Now, if you had a standard window, you don't see the other one. You go, where's my other graph? Well, remember this, as we saw, has an initial value of 16. Our window only goes from up to positive 10. So if we adjust our window a little bit here, we want it to at least get up to 16. So let's go to 20. And, oh wait, that's our x value, which we want to go out to 15 minutes, right? So at least 20. 15 didn't get us quite far enough. Let's see, what's this, right? X value is time. Let's see what it, after say maybe 50 minutes. What we want is our Y maximum. This is our temperature. We want it to be at least 20 so that we can see our initial value of 16, right? So now when we come back to the graph, we can really see everything. We see the 16. We see, if we leave it in the refrigerator too low, it's going to get really frozen. It's going to get below 0, ice. But what it allows us to do is see this intersection point is the solution for when it's exactly 3 degrees. And then we're going to take it out and drink it. So the way we find that is we look for second calc. Notice it's in blue. So I'm going to pull up these tools. There's a tool called intersect here. So I'll do number 5. It asks for the first curve, and it's already this little flashy guy. I call him a little spider guy. It's only got 4 legs, but close enough. Maybe those are double legs, so we could call them 8. It jumps, once I set enter, it asks for the second curve, and it jumps to the second curve. I'm going to put enter. Now it asks me for a guess, so I hit enter one more time. And notice the spider jumps to the intersection and tells me it takes 27 minutes, 27.86, for it to become 3 degrees. So I'll set my timer for maybe 28 minutes, right? But what we just did is we solved for x, 27.86. Let's round that to the nearest minute. X equals, well, 27.9 minutes. Close enough, right? 28 minutes. But that's how you can solve for an x graphically. And again, in the next few lessons, we will find algebraic methods for doing that using something called a logarithm, which you'll learn about in lesson 11. So that is our lesson for Module 10. And oops, turn back to the slideshow. And so now you're ready to go ahead and do the activities in Module 10. Remember, we do have our online tutoring. We have a structured office hours. You're welcome to come visit, contact me, and then through the discussion forums, the Inscribe and such, we have how you can work with peers and other tutors. So keep moving forward and do those activities. Thanks.